So I think it fits at least a little bit. Thanks for coming. So I'm going to talk today about how to compile ML modules. I have some sort of background here, which in an ideal world, none of this would be necessary, but I'll run through this. So ML modules is this mechanism for programming in the large that's featured in languages like standard ML and OCaml. And there's two main things that go on in ML modules that are interesting, right? So they're something called structures, which combine types and terms, and so that gives you abstract types usually, and then operations on those types. And there's functors, which gives you a mechanism of reuse, where you can have some code that depends upon something else, and you want to fill that thing in later. And one remark that's important for today is that, so this is not just a mechanism for namespace management, right? So a module, when opaque, can only be accessed through its interface, right? So you have to use exactly the operations that are provided to you, and no others. And these functors, they reuse code in a parametric way, so they can't depend upon internals of the things that you're depending on. So as I said, today we're going to talk about how to compile these. And of course, we've been compiling ML modules for some time. Today I want to talk about typed compilation. So I should just remark that without types, how to compile modules is a fairly well understood problem. You just pretend that they aren't modules anymore. You erase all the types and just compile as core, and I guess that's fine. But I think types are valuable in compilation. First of all, and this is maybe what motivates me the most, I think without having the types there, you don't really know what's going on, right? So having the types there circumscribes how we're looking at these things, and without that, we don't really have a good understanding of what our compilation is doing. On a more practical level, it's very useful to have these types when you're implementing a compiler. They're very good at catching, not all, but a wide array of compiler bugs. And without types, you could very rarely have at least interesting contextual equivalences. There's just too many different experiments one could do on a program if you don't have types, and you're able to detect differences that you shouldn't be able to detect. Okay? And so in particular, the sort of full abstraction result I'm going to talk about today really depends on types for you to be able to even start talking about that. Okay. So just some terminology to make sure we're all on the same page. So contextual equivalence, I think it's phrased in an earlier talk today. So this is sort of the gold standard in program equivalence, and you're going to say that two programs or program fragments are contextually equivalent if there's no experiment that you can do that can distinguish them. So whenever you embed them in some larger code, you can't distinguish these two things. All right, so that's what contextual equivalence is. Full abstraction says that if two programs are equivalent, if and only if, once you translate them to the target language, the translations are equivalent, right? And so you're not losing, or I suppose gaining, but you're not losing any abstraction as you go from the source to the target. And so this is the strongest correctness statement that we can make about this translation, saying that the translation is really reflecting exactly all the abstractions that exist in the original program. And so a programmer who writes a program and then it goes through a fully abstract compiler, knows that any abstractions that are in his or her original program are going to be respected. And that's even if you link in code from some completely different language, again, assuming that everything is typed. Right. Okay, so what's this work? So what I want to talk about today is a type-preserving translation for ML modules. The underlying module language has the full array of features that we need to explain what's going on in standard ML. So there's structures, there's functors, there's translucent signatures, which are signatures that have some additional type specifications built into them. And there's sealing, which is really important to what I want to talk about today. So we can make a module opaque. There's also a bunch of other features that we support in this that aren't needed for standard ML, but are also useful and used in some other languages. So this is the first translation for modules with any kind of dynamic correctness result. Right? So in previous work, we could say that translation provides a well-typed target program, but now we can say that it actually provides, in some sense, one that does the right computation. All right? And so the sense in which we want to say that these things, translation is dynamically correct, so we want to say that the resulting program is contextually equivalent to the original program in a sense that we'll have to make precise. So that means that then that there's no experiment, and again, what sorts of experiments we'll have to make precise, but there's no experiment that you can do that'll distinguish the target program you translate to from the original program. All right, and this is good because it means that this correctness holds up however you use the resulting code. You know the resulting code really is the same as the source. And so you could do what's called vertical composition, which means maybe I run that through the rest of the compiler, or I compile other things away. That's pretty likely. Or horizontal composition, where I combine that with some other code that wasn't the code that I translated. And also, we're going to be able to show that this translation is in fact fully abstract, and that result's going to be a corollary of dynamic correctness. And also I want to remark, although I'm not going to really dwell on this, that the translation that I talk about here admits separate compilation. If you didn't insist on admitting separate compilation, then there's other things you can contemplate that wouldn't work if you wanted separate compilation. Okay. All right. So I want to start then by talking about phase separation. This is actually a near and dear topic to my heart because the first project I did as an undergraduate, my first research project, was working on phase separation. So the idea of phase separation is you take a module and you break it into what's called the static portion and the dynamic portion. So the static portion has type-ish stuff in it, and the dynamic portion has term-ish stuff in it. And the important thing is that the static expressions cannot depend on the dynamic expressions. All right, so dynamic can depend on static, but the static stuff can't depend on the dynamic stuff. And for this to actually work, I should remark that it requires some constraint on how modules are used in the language. So this motivates Standard ML's notion of second-class modules. You can have first-class modules, but then you need some other sort of strictures on how you're going to use them. Okay, and what Harper, Mitchell, and Moji were interested in was this idea of a phase distinction, which is to say that there's two phases when we're considering the semantics of the language. There's the static phase, which is basically type checking, okay, and then the dynamic phase, which is compilation or execution of the compilation. And the idea is the static phase should never depend upon the dynamic phase, meaning in practice that you can type check code without ever having to run any code. And if you look at the way ML modules combine types and terms, it's not a priori obvious that that's the case, but you can show that that's the case. And in their setting, they showed that if you deleted all the dynamic equations from the equational theory, the static equations would still hold. And none of that matters to what I'm going to talk about today. So today I'm interested in the phase separation process in its own right as a strategy for compiling modules. Okay, so let me talk about some prior work in this area. All right, so first there's, again, Harper, Mitchell, and Moji. And one way that isn't suffice for what we want to do now is they didn't consider any kind of sealing or generativity. Okay? Subsequent to that, Zhang Xiao had a paper that did support sealing and generativity. In other ways, it was actually pretty similar to what Harper and company did. But the way that they dealt with sealing was they just erased it. All right? And so it's not going to preserve abstraction in the kind of way that we want to talk about here. Another thing I should mention is, so Elsman in 1999 had a really radically different idea for how to compile modules. They called static interpretation, and there the idea is all the module computation, you'll resolve all that at compile time. So if you apply a functor to arguments, then any computation that results from that, you're just going to do that at compile time. And so in the sense, the terminology I was just talking about, what you're doing there is you're weakening the phase distinction, right? So then the static phase is going to depend on some things that you're used to thinking as dynamic, right? Certain aspects of executing module code. And then the most relevant to what I'm going to talk about today, I would have on the next slide, is Ken Shan in 2006, and Rosberg, Russo, and Dreyer in 2014 had a compilation strategy that's actually fairly similar to what I'm going to talk about. All right, so what they did is they wanted to compile sealing using existential types, which, at a first glance seems like it completely makes sense, right? So existential types give you data abstraction, and so using those to explain data abstraction seems like a good idea, right? And it is a good idea. I shouldn't imply that it's not. And their translation, if you kind of squint at it, is basically the same as what I'm doing here, all right? I guess I should mention, although I'm not going to dwell on this, they actually supported something called weak sealing, which this work doesn't, and you can ask me why, but I otherwise wasn't planning to talk about it. One thing that's important is that the presentation of that work does not look like phase separation. Right now, on some level, that's just a cosmetic thing. I really like phase separation, and so I prefer to present it that way. But what we'll see in this talk is it actually really matters to the way the correctness proof works that it be represented as phase separation. Also, neither of those actually had any kind of dynamic correctness result, and there were some good reasons for that. They, in some sense, actually couldn't with what they were trying to do, but they didn't have a dynamic correctness result, and in fact, I'll show here that they were not, in fact, fully abstract. Okay. All right, so caveat, this talk is full of lies. I can't do this right without developing some notation that I just don't have time to develop. So this is supposed to convey the idea, but you'll have to go to the paper for the actual details. All right. The one thing that I do have to talk about, and this is, I think, why this paper did end up in this session, is this idea of sealing as an effect. So this is important. So whenever I seal a module, which is to make it opaque so you can't access it except through its interface, we're going to consider that to be a dynamic effect. And you could think of this as some daemon comes in and fiddles with all of your type components in such a way that you don't know what they are anymore. You can't tell that it's changed, but you don't know what they are anymore. So there's some dynamic effect that's taken place there. And if you have first-class modules, that could even happen. But otherwise, it's a notional thing. Okay? And so in our type system, that's reflected in the type system. So there's two different judgments. There's a pure judgment that says this module, M, has signature sigma, and it's pure, and the other one says it's impure. So one of them says it's sealed, and the other one says it's unsealed. Or I guess the second one says it might be sealed. Okay. All right, so I have two pretty technical slides, so bear with me here. This is the first of the two of them. All right, so the way the translation looks is, so a signature is going to split into two parts. All right, so the first part is this K. That's the kind of the static portion of things that would belong to that signature. And then tau alpha, that's the type of the dynamic portion of things that would belong to that signature. And there's this dependency. The dynamic portion has to be able to refer to the static portion through this binding. So it's alpha colon K dot tau depending on alpha. All right? And so so K should be a kind, tau alpha should be a type. When I'm translating a pure module, then we see things that look like phase separation. So M turns into C comma E. C is the static portion of the module, and E is the dynamic portion of the module. And accordingly, C should have the kind K, E should have the type T, where we put in C for that dependency. All right, so for impure modules, things work differently. Impure modules, we don't know the static components statically. They're not really static anymore, because this daemon might fiddle with them. All right, so we're going to produce an existential package of the eventual static component once we know it, and the dynamic component. Okay. All right, so I'm running a little bit behind schedule, so I'm just going to run through this quickly. This is the big technical slide. I'm just going to lose most people on this slide anyway. So, but let me briefly run through this. All right, so atomic signatures, they turn into something which is degenerate on either one side or the other. So the unit signature is degenerate on both sides. Okay? If I just have a static component with some kind, then we have a non-trivial static component, but the dynamic component is degenerate. That's unit. And vice versa, if I just have a term field, then the static component is 1, but the dynamic component has some type. Okay? And so these rules for phase-splitting structures and applicative functors are actually taken directly from the original Harper, Mitchell, and Moji paper. All right? For generative functors, then what we'll see is generative functors have no interesting static component, right? Because they're generative, right? You can't tell what they're going to do statically. And so they take in the same sort of material. They take in the static and dynamic component of the argument, but then they return an existential package of the static and dynamic component of the result. All right. Okay, so what I really want to talk about today with the time I have left, which is actually not that much, is how does dynamic correctness work, right? So the big trick here is I want to say that this original program is contextually equivalent to the translation, but they have different types, they're in different syntactic classes, and indeed they're in different languages. So how do I even say that they're contextually equivalent? Well, the different languages problem we can deal with by the fact that the target language is a subset of the source, so we just look at everything in terms of source, and that's fine. But to mediate the types, then we define something called first, second, and join. So first and second are things that take apart a module and give you its static and dynamic component. The terms first and second are just borrowed from terminology from earlier papers. Join would put them back together to get a module. Okay? And what's important about these things is that they're defined in the language, right? So what they don't do is use the translation and go through the module and figure out what the static and dynamic component is. They're just mediating the interface. Okay? If they actually did the translation, then this result would be trivial, right? So we can show then that these are in appropriate sense inverses. So if I take a module M and I split it into first and second and I join that, that's contextually equivalent to M. And conversely, if I have C and E, which are appropriate to be the static and dynamic components of a module, and I join them together, and then I take second to get back the dynamic component, then that'll be equivalent to E. Okay? And this second one I'm going to come back to. This one is actually pretty tricky, the second one. We need both of these for the full abstraction result. All right, so how does dynamic correctness work then? So for pure modules, we say that if M splits to C and E, then M is contextually equivalent to if you join C and E together. All right, so that's once you've set everything up, that's just what you'd expect. For impure modules, it's a little bit more baroque, but the module is, well, if I take this existential package E, I unpack it into the static and dynamic component, and I join those, then that's going to be contextually equivalent to the original module. Okay? So this is dynamic correctness talking about things on the target, on the source side. We can also do a target side where we're talking about the terms E as a corollary. Okay. Now I need to make a remark here that's important. So there's two different languages, the source and the target, and they then each have their own notion of contextual equivalence. Okay? Now, if you have equivalence in the source, that implies equivalence in the target, and that's trivial because the target is a subset of the source, so it has strictly fewer contexts you can look at. All right? The other direction is also true. If things are contextually equivalent in the target, they're contextually equivalent in the source, and that's should not be at all obvious. All right? So if you think that's not obvious, then you're right. But actually, there is an elegant proof, and it just uses the other things that I'm talking about here. It's not some horrible thing where you got to go through everything all over again. Okay, so then the proof of full abstraction, right? Then it's pretty simple. So if Mi splits to Ci and Ei, and let's suppose M1 and M2 are contextually equivalent, then E1 is contextually equivalent to the second of M1. By congruence, that's the same as second of M2, which is E2. Okay, so that gives you the left to right version, and the other version is basically the same. M1 is contextually equivalent to joining the static and dynamic components. If you replace them with contextually equivalent static and dynamic components, that's the same, and then you can put it back together. Okay, so once you set everything up, everything falls together swimmingly. All right, now the tricky part of the setup, and this is the last major point I want to make, is that so recall that if I take join and second, that should be equivalent to the original E. Well, this, it turns out, requires us to put a value restriction on the body of polymorphic functions. Why is that? Well, if I do second composed with join, it turns out, if you look at the code, that does a big eta expansion. And so consequently, F should be contextually equivalent to lambda alpha, lambda x, F alpha x. And it turns out that those actually, I mean, I can't just put in bottom for F because that F has to be a value, but I could put in lambda alpha dot bottom, and then you could distinguish both of these things, at least if you have any kind of strict feature at all, which ML certainly does, and even lazy languages these days have seek, which would be enough to make this observation. All right? So we have to rule out this idea of putting in lambda alpha dot bottom for F, and so to do that, we put in a value restriction in the static semantics for the language. Right? And this is why previous translations weren't fully abstract. It wasn't actually anything to do with the translation, which was fine. probably. I didn't prove it, but probably fine. But with the target language, right? So because there wasn't a value restriction in the target language, they weren't able to work that way. Okay. I can skip that, and I can skip that. So all this stuff is formalized in Coq. It builds on the work that I presented to Popple 2 years ago. So 80% of the Popple code, roughly speaking, was able to be reused. And also, just as a sort of a coarse notion of how important this value restriction is, putting that into the Coq code took less than a day. So it didn't really change all that much to put in the value restriction. So, and I think that's it. Thank you.
Okay, we have time for a couple questions. I'll lead off with one from Slido, from Anonymous. What about a rule for first of join? Why do you only mention second of join?
I'm sorry.
What about a rule for first of join? Why do you only have
first?
Second?
Yeah, first of join. That one works too. It wasn't really important for the story I was telling, but yeah, that works too.
I was glad to see you mention the value restriction for big lambdas. For very, very different reasons, work that we did on gradual typing, we had to introduce exactly the same restriction. It makes things like erasure easier. And I've come to the point of view, which I'm hoping this community will adopt, that the original definition was a bug, and we should always have had the value restriction there. Of course, ML has the value restriction in order to deal with effects.
Yeah, I tend to agree with that. I mean, it's hard to put a really sort of crisp bow on it, but it just keeps coming up for a variety of different reasons, which argues that maybe that's just the way we should look at it.
Value restriction, yay.
Okay.
Did we have one more question in the back?
Uh-oh.
Hello? Yeah, okay, there we go. Can you say a bit about about weak sealing? I'm curious just because without weak sealing, for example, if you have a functor with a data type definition in it, then it has to be generative.
Yeah, so weak sealing, right. So I didn't handle weak sealing. So I think that the translation of weak sealing in Shan's paper and in your paper, I think that probably is right. But we couldn't even start to look at that, right? Because you need to have some notion of what the equational theory is for weak sealing before we could start talking about things being equal in the presence of weak sealing. And that's what I don't know how to do. So the work that I talked about 2 years ago, talking about contextual equivalence for modules, if you have weak sealing, I just don't actually know how to do that. If you have an idea, then I think that that this stuff would probably port to that, but I just don't have the lemmas I need or even the definitions.
Okay, I think that concludes this session.